Hi everybody, welcome to my next episode on climate change calculated, this time a Corona update. My name is Gerald Schuller. So first take a look at the climate change. So many people might have forgotten that we already had a record warm winter, right? So this winter was actually quite unusual, and most will probably remember that we had almost no snow or frost. And this is also captured in this article here by The Guardian. This winter in Europe was hottest on record by far, say scientists. So here they also have some data. For instance, Europe's winter was 3.4 degrees Celsius hotter than the average from 1981 to 2010. And in Finland, the average temperature for January and February was more than 6 Celsius higher than the 81 to 2010 average. So that's quite considerable. And this is also an interesting satellite image here, which shows that most of the Earth got warmer in the winter. So you can see white means no change compared to the average, long-term average. Red means above average and blue means below average. And you can see almost the entire Earth is above average. So that's unusual. Usually you have equally distributed red and blue, but now it's basically all red. Only a few patches of blue. So that's quite unusual. Also in Antarctica, the temperature rose above 20 degrees Celsius for the first time on record in February. Almost a full degree higher than the previous record since 1982. So also Antarctica is getting a lot hotter, and this can be seen also here in this part here. Okay. And also what's interesting is that during the corona restrictions, the air becomes noticeably more clear. Less pollution, less CO2 in the air, and more sunshine, which can be seen in these links here. So you can see NBC News, and they have some examples here. And here you can see Venice with all of a sudden clear water in the channels because of no boat traffic anymore. And this is also interesting. This is a satellite image from China, which can be seen more clearly here. So here you can see the nitrogen dioxide, which plummets over China during the shutdown. So this is before the shutdown. So we see vast areas of high concentration of nitrogen dioxide. And then after the shutdown, basically everything is gone. So this shows that the impact that people have on the air quality. So it's actually a lot. So this shows the short-term effect of air pollution and the removal of it. So it actually tells us we can do something about the air quality. And that's the important lesson here. So now an update on the coronavirus. So despite the start of spring in March, the new coronavirus continues to spread all over the world, unlike the common flu. So the common flu stopped by now, but the coronavirus is still going on, and that's bad, which means it will continue in the coming month. And so things are getting worse. There are questions how it compares to the common flu, right? As I just mentioned, the flu would be over by now, so this is one of the differences. But there are more differences when you look at a few virological and epidemiological parameters. So the first important parameter here is the basic reproduction number, R0. Right? You can read more about it in this Wikipedia link. And basically, this is the average number of persons that an infected person infects. So this is what we can influence, for instance, with social distancing. The second important parameter is the so-called serial interval. You can also read about it in this Wikipedia link about the definition. And this is basically the time over which these infections appear. So basically the time over which a person is infectious and spreads the disease. So this depends on the virus. So we have a certain period in which we are infective, and in this period, on average, we can infect this number R naught number of persons. So this is what we can actually influence. So combine both R naught and the serial interval T, we can compute our daily factor of increase, F of our model. So in our model, we use purely statistical parameters, which are much easier to estimate than R naught and the serial interval. This is basically inherent for each virus, but we can directly observe our daily factor of increase from the data. But if we have R naught and the serial interval, we can also compute this daily factor of increase for our model using this formula. So R naught, the average number of infected people, is F, our factor of increase per day, to the power of T, the number of days in which we are infective. So T is this the serial interval basically. So then we have this formula R naught to the power of 1 over T equals F. Right. So easy formula, and we can use that to compare different viruses. So the first one is the current new coronavirus with a scientific name SARS-CoV-2. And here in this Wikipedia link from the Robert Koch Institute, we have a few parameters. So it lists the R naught as between 2 to 3.3. So I assume the average, which is 2.7 for our comparison. Then we have the serial interval, which is listed as between 4 and 7.5 days. And I again assume the average, which is 5.7. And that gives us a daily factor of increase using our formula, 2.7 to the power of 1 over 5.7 equals 1.19. And the 2 stars here is the Python notation for exponentiation. Yeah, and then the mortality rate of SARS-CoV-2. So here I have a few links which give data, and they give a range of about 0.6% to 5%. And for my model, for the long-term prediction, I assume a 2% mortality rate. And also checked it from a country which has good testing, which I hope we will also have in Germany. And this testing is there used to isolate infected. And they also have good hospitals, so they give good care to people. And they're actually the case number stabilized. So it's more easy to estimate the mortality rate, because you can assume that basically everybody was counted. So in South Korea, we see on April 1st, we have 165 deaths. And 16 days ago, on March 15, we had 8,500 cases. So the 16 days are my assumption from last time, that it takes about 16 days from being detected to either recover or die. So I just need to put the 165 deaths in relation to those 8,200 cases, and we get an estimated mortality rate. Here I make the division, and this is 2%. So it's actually quite fitting. So that's why I chose this 2%. So now we can compare it with the seasonal influenza or the seasonal flu. And here in this link about the basic reproduction number, we can also see a table where the seasonal influenza occurs, and it gives an R naught of in between 0.9 and 2.1. So this is actually less than we have for the new coronavirus. So on average, people infect fewer people. So I assume the average 1.5. Here the serial interval is about 3 days. So the period over which people are infected is shorter than for the new coronavirus. And this results in our daily factor of increase. 1.5 to the power of 1/3 is 1.14. So somewhat less than for the new coronavirus. And what's the bigger difference? The low fatality rate. Here we have a fatality rate of only about 0.1% according to these links here, which is about 1/20th of my assumption for the new coronavirus. So another interesting comparison is actually the Spanish flu from 1980, the pandemic. So again, here looking at this Wikipedia page about basic reproduction numbers, it also lists the 1918 pandemic strain as R0 equals 1.4 to 2.8. So let's assume 2.0. I also found the serial interval from this web page. It's 4 days. So these numbers or parameters are mostly estimated from data from those days. So it's actually quite interesting. So that gives us the daily factor of increase for the Spanish flu of 1.19. So we see it's actually basically identical to the factor of increase that we have for the new coronavirus and higher for the seasonal flu. And we can also estimate the fatality or mortality rates. I found it here in these links. This New York Times link is actually quite interesting. It gives quite an interesting story and data about the Spanish flu. So the Spanish influenza is estimated to have case fatality rates above 2.5% compared to less than 0.1% in other influenza pandemics. So here we have a number for the fatality rate. So from these data I made this table, which you can see here, which compares the Spanish flu, the seasonal flu, and our new coronavirus, SARS-CoV-2, with respect to R0, the serial interval, the daily factor of increase, F, and the mortality rate. So for us, most important are the last two columns. Here we can see that the daily factor of increase is very similar, particularly between the Spanish flu and the new coronavirus, and slightly less for the seasonal flu. The biggest difference is indeed here in the mortality rate. You can see the seasonal flu has less than 0.1%, and both SARS-CoV-2 and the Spanish flu have around 2%. The Spanish flu is somewhat higher, but both are significantly higher than the seasonal flu. So this is what we can learn from this table. Another interesting fact that I found is that the Spanish flu only spread from people with symptoms, but SARS-CoV-2 spreads from people before they show symptoms. So that is bad. That it makes it significantly easier to spread and also makes corona tests essential. You can imagine that the Spanish flu, you automatically had a built-in test when people showed symptoms. If they showed symptoms, they needed to quarantine, but if they didn't show symptoms, they also didn't spread the virus. So everybody who didn't show symptoms could walk around without harm. This is different now. Now we have many people walking around not even knowing that they have the virus and spreading it. And that makes it so tricky, and that makes it so important to have corona tests, so that we can find everybody who spreads the virus. Yeah, further important difference, for the seasonal flu there are vaccines, and a good portion of the population has immunity, which limits the number of susceptible people and the spread, which is good. So only a certain fraction of the population is susceptible to the flu each year. But for SARS-CoV-2, the new coronavirus, everybody is susceptible, which is bad. So that's the entire population. This is also similar to the Spanish flu or the Native Americans after the arrival of Europeans, who mostly died of the flu or cold because they had no immunity. Their immune system never saw flu or cold before, and that's why they had a very high fatality rate. Okay, so now let's review and update my model with the data from March. Right, now we have the beginning of April, and now it's a good time to review and update the model with new data. So the Johns Hopkins University maintains a practical GitHub repository with their data. And I use Python pandas to read in the data to compare it with my model with these commands. So this is for people who like data and Python. So here is this library pandas, which I use to read in and extract the data. And here this URL lib is used to access the GitHub repository on the internet. So here is the URL, and then here with URL lib request URL retrieve, I read in the data. So this is a table which was read in, and then here using this pandas command, I basically take this data and convert it into a pandas format. So here it reads the data and stores it locally in this file here, and then the next command reads from this local file and stores it in this variable df. And then using df I do my comparisons. Yeah, so now we can let the program run with Python 3 corona cases review.py. And this program here is in the website that is linked below this video. So below the video you can find the link to the website where you can download this program. So you can actually try out and see and compare the plots, and also modify it for your own data, for instance, for different countries. So this program first prints a numerical printout of the data that I'm using. So for instance, if I just want to know the data at a certain day, I can just go to the terminal and then see that number without going to the plot. After that, it plots the number of detected cases and the recovered. So here you can see it. So here in this plot we can see a comparison of my model's prediction and the data that I downloaded from the Johns Hopkins University. And this is the detected cases. So this is the cases that are really measured, and blue is what my model predicted. And we can see both data for Germany. And you can see in the beginning it was actually quite nice. Then here before March 20 the real cases were actually rising faster than my model, but around March 20 you can see it's flattening. So here it's becoming now considerably less than my model. And this is actually really interesting to observe, because March 20 was the weekend where the more severe restrictions were imposed in Germany. So here you can really see this kink here, this flattening of the curve, which is the effect of the restrictions. So you can see actually they indeed work. It's just a question if they work enough. So nice flattening of the curve here. So that's a nice success. So that's a good part. Then we can also compare the predicted and detected recovered cases in green and red. You can see here in the beginning of March there was a nice fit, but then around March 23rd we have a much stronger increase in the number of recovered cases. So probably people didn't recover faster than before, but probably they were just detected later. So that's why those persons who recovered here were not counted before. So that's why we have this sudden rise here. So that means that my estimate of 16 days between detection and recovery or death from previous time probably became less. So I need to check it. Yeah, and also when we compare the value on March 30 between infected and my model, you can see here this difference here. This is the number of infected that the countermeasures here saved, right? And we see it's about 70,000. So the social distancing indeed already saved about 70,000 infections until March 30th. And this number becomes bigger and bigger, right? So here this gap increases when we go on. So this is already quite a nice success. We already saved 70,000 people from being infected. Yeah, so next observe the recovered cases. So as I just mentioned, on March 23rd, the number suddenly increased. And this comes probably from a later detection, as I just mentioned. So this is also related to the death cases. So now we can also compare the death cases from my model and the detected cases in Germany. So here the orange one are the detected cases and the blue is the predicted ones from my model. And here you can see the real death is considerably more than my model. And this is also connected with this sudden rise in recovered people. This is probably because the detection came later than before. So before we had those 16 days and now we have fewer days, and this makes my model imprecise. So we need to update this number from detection to recovery or death. Yeah, so this is what I do here. So we can estimate the time from detection to recovery or death from the data, which shows in the terminal output of the program. So this is what it lists first. So I take the data from late March because there the numbers are higher, and when we have higher numbers, it becomes more precise. So on March 31st, we have 16,100 recovered cases and 775 deaths, so a total of 16,875. So now we need to find a similar or higher number for the detected cases to see where they came from. So I found March 19 has 15,320, March 20 has 19,848. So it's kind of in between those two. And that's why I decided to choose 11.5 days, because from March 20 to 31 it's 11 days, and to 19 it would be 12, so I chose the middle. Right, so you can see it shortened from 16 days in the first half of March to just 11.5 days in the second half. And I could imagine that this is because of the strong increase of cases in the middle of March, where they couldn't increase the number of tests accordingly. So they only tested more severe cases. So then I updated the time from detection to recovery or death in the program and plot again to see if it fits. So now you can see it again. So what changed here is the lower green line. This is what changed now, and you can see now the green line is a much better fit to the detected recovered cases. So this actually gives us a good fit. So the 11.5 days seems to be more or less okay. So now we can compare for the death cases in March. So here again the detected cases, the death cases, and blue is now my model. So here about March 25 it's okay, but then it's underestimating a little bit, but I'm happy with it, so I keep it this way. Using these numbers, the 775 deaths, 16,100 recovered on March 31st, we can now also compute a detected case-based mortality. So basically just depending on those cases, which is the fraction 775 divided by 16,100 plus those 75, so the total number that are present, and this is 4.6%. Right, and this is higher than the infection-based mortality rate of about 2% because not all infected are detected. Right, and this also means that we have an underdetection rate of 4.6% divided by 2% equals 2.3, which is actually not too bad. So that means the true number of infected should be roughly a factor of 2.4 higher, or say 2.3 higher than the detected cases. And this depends on the testing rate. The testing rate is also quite different in different countries, and I found this interesting table about it. And we can sort this table for tests per million people, and there we can see that Germany is actually in a relatively good position. So I can actually open it. So then it opens this Wikipedia page, and when we scroll down, here's the table, right? And if we now click on tests per million people, then it orders according to the number of people tested per million. So if you click twice, then the best is on top. And here we can see that Iceland is top with 64,000 tests per million people. And when we go down, here New York State is also quite good. New York State in the USA, 14,500. And here we have United States, Los Angeles is also quite good. And here comes Germany with 11,000 tests per million people. So we are actually quite good. Also here there's Washington State, also one of the first states affected by the coronavirus. Here we have Hong Kong, 12,000. Hong Kong was also very early affected. Italy, very heavily affected, has 14,000. So you can see all the countries or areas which were early affected have high number of tests, or those places which took precautions. Right, so this is actually quite an interesting table. Yeah, so you can check it out yourself. So what's essential for prediction is our factor of daily increase, the F factor. And using our data, we can now compute and plot the daily factor of increase F for the detected cases and for the death in March. Right, so I'm taking this the data from the internet, from the GitHub website, and now you can see this factor of increase over the days in March. And here first blue, the factor of detected cases. Here you can see in Germany in the beginning it was between 1.2 and 1.8, although here the numbers were quite low, so it was this is an inaccurate estimate. So later here it stabilized around 1.25. So this is basically the factor I used for my last model. Here it fluctuated a little, and then after March 20 it suddenly became clearly lower. So now we are around 1.1 and here below 1.1. So this is a good sign. So we are in a good way here. And we can see that this factor for the number of deaths has a similar shape but delayed by those 11.5 days. Yeah, right. So when you look at the numbers, we see that on March 31st, we now have this factor of 1.075, 1.075. So this is actually much better than before the 1.25. So now assuming this factor of 1.075, how many days does it take to obtain a doubling of the numbers with this factor? So here's the formula. So this should actually be 0.75, and this should also 0.75, and here should be a 0.75. So when we plug it in, we get 9.6 days. So using this factor here, this factor of increase, we can compute that we will get a doubling every 9.6 days. So that's much better than the 3 days that we had with this factor of 1.25. So we can now also compare this factor of increase f for different countries. It's also quite interesting. Here I included several countries and also South Korea, which is kind of a role model for us. So Germany is orange, you can see here. Germany is down here. So it's actually not too bad. Spain, which is actually worse affected than Germany, is actually a little bit above Germany in this factor of increase, so that's bad. Italy is better than us. So here Italy is worse affected and they also have a lower factor of increase, so their measures work. But the lowest is South Korea. So here you can see it. And South Korea, actually, when you look at the numbers, they have this factor of 1.02, which is what I found last time is necessary to delay it enough to have vaccines to avoid all the death. On the upper end you can see Russia. It's actually going up. And red is Brazil. Brazil is getting worse. And the US is kind of in the middle. So the measures in the US as a whole are not really working that great yet. We can also zoom in to the lower right part to see it more precisely. So here we can now see it. Down here we have South Korea, so with this factor of 1.02. Above we have Italy, which has about 1.04. And then comes Germany with our 1.075. Right, so we are good, but not yet good enough. So South Korea indeed achieved my target of 1.02. Yeah, and these updated numbers and a new data point at the beginning of April are now used to update my model to make predictions for Germany for April. So first, the number of detected cases. You can see it the day after beginning of April, so until the end of April. And here you have the detected cases, the case number, and orange is the recovered cases. And you can see soon we will reach the 100,000 infected people, and then mid-April we will reach 200,000. Then towards the end of April we will reach 500,000. So all assuming that we stick with this 1.075 factor of increase. So this is an extrapolation for the case that we don't change anymore. Next, the concurrently sick. So here you can see the month of April. And here is the number of people who are sick at the same time from the coronavirus. So these are the people who show symptoms or who are spreading the virus. Yeah, this is interesting for the rate of intensive care. So according to this link, it says that the infection-based mortality is 2%, as I assumed earlier, and the rate of intensive care is 5%, a factor of 2.5 higher than the mortality. So if we have the mortality, we can compute the case-based intensive care. So this means we get a case-based rate for the intensive care in Germany of 2.5 times 4.6%, about 12%. So according to this link, we have about 15,000 intensive care beds reserved for corona cases in Germany. If 12% of the currently sick require intensive care, this corresponds to 15,000 divided by 0.12, which is 12,000, which is 125,000 currently sick cases. So this means if the number of currently sick cases reaches 125,000, our intensive care units reach their capacity. And when we look at the plot above, this will be around mid-April, and that's bad. So when we look back here, so April 15 has about 125,000. So that's still too much. So that means we need to flatten this curve further, so that we don't reach this point where the intensive care units are overwhelmed. Right, so to avoid this daily factor of increase of 1.075 needs further reduction. In my last video I concluded that the factor needs to be at f equals 1.02, which means a doubling in 35 days. So just once a month there's a doubling. It's still a lot, but this is more manageable. So here's the number of deaths in April. And here we can see that in the last 20 days, from 10 to 30, we get roughly 10,000 additional deaths, which means about 500 a day. And that's a lot. So now to the long-term prediction. So using the parameters from the beginning of April, we can now let the model run for a prediction over 150 days, starting April 1st. So first the detected and recovered cases. So this is the plot of detected and recovered cases. And you can see here, after around, let's say 140 days, pretty much everybody is infected, right? So this is bad. This is actually too fast. And that this is bad is clearly seen in this next plot about the concurrently sick. So here we can see that around 100 days after the beginning of April, so early July maybe, we get this maximum of about 16 million currently, or 70 million people sick at the same time, right? So this is the big peak, and this is too much to handle. So this is much too much, these 17 million people. So we don't want that. So that's another argument for saying we are not there yet. Here the death cases. It's also interesting. Here we can see the death cases after about 140 days rise to about 1.6 million. So here. So that's also much too much. In comparison, a very bad seasonal flu year in Germany has an excess mortality, which is all death above the long-term average of about 25,000. A normal flu year just has 200. So this number is also independent of the rate of increase and only dependent on the infections-based mortality rate, which are assumed to be 2%. Right? So the 2% is basically what determines this final outcome. But different sources give different ranges of mortality rate. So if you assume a mortality rate of 0.6% to 5%, then this number would be between 498,000 and 4.15 million deaths. So in either case, it's much too much. So even the 0.6% we cannot handle. So hence it is best to slow the spread until we have a vaccine. So that's an important lesson here. We need to spread it until we have a vaccine, basically. Yeah, so this shows that we really need to reach the daily factor of increase of 1.02, which is a doubling in roughly 35 days, which I showed in my last video, with social distancing and also with comprehensive testing to effectively quarantine each infected person, like in South Korea. South Korea could also be a good role model because they reached this factor and managed to almost stop the spread without much restrictions, so mostly relying on testing. So that leads me to my conclusions. Mathematical models, data and programming allow effective predictions. We are now on the right track, slowing the spread of the new coronavirus, but not quite there to avoid overloading our hospitals. We need to slow the spread until we have a vaccine to avoid the high death counts. An important part of a solution to slow the spread is comprehensive testing, as in South Korea, which allows loosening restrictions. So this is also important for our economy. Okay, so that's it for today. Thank you for your attention. Like my channel and yeah, stay healthy. Bye bye.